Okay, so yeah, so we're talking about particle choreography today, and I don't know if I have a web browser. Let's see. I do, Chrome. So I actually was working on gravitational operators, and I was like, cool. And I learned a few things about doing this. So yeah, this can be done in an hour, technically. So I think I only have 100 particles here. This is all that's going on. I think it's kind of interesting how they kind of migrate. I was wondering if there was going to be like a I kind of like implemented flocking in a way, just kind of. But this is just using the.
So every particle is affecting gravitational pull on every other particle.
Yes.
Okay.
In fact, it is actually going n squared because it's doing. I probably could maybe make it a little bit more efficient, but honestly, if you have an n squared algorithm, it's going to be n squared. And so unless I'm getting like a log n improvement or something like that, there's just only so much that you can do. So we're actually talk a little bit about how this particular case is handled. I was trying to let's see here. Let me go to the code. The fastest way to get your computer back to normal is to minimize your browser, because it won't render a frame while the browser is minimized, unless you force it somehow.
So it does still consider the time step all the way up. I remember like the simulation. Stuff like that. Just like
yeah.
Fast at that point.
It does do that. So let me go to example 8.js, and I think currently I have it at 100 objects, but I think I was trying to make, go back up. I was trying to experiment with, what if I make a big one in the middle? So let me save that, and let's see if I can create a big one in the middle. Or I did make a big one in the middle. Let's go back there again and see why that's the case.
Actually, they can impact each other. Walmart.
What's that?
So now you just need to make them impact each other in Walmart.
Well, I actually did do that initially.
Made it worse.
No, not necessarily. So let me see here. If I do this dot detect, I think that this will. Oh, okay. There was the big object. I'm gonna get rid of the big object. This is the kind of thing you get lost. You get the reset function. You get lost doing this. So I guess one of the nice things about if you add an n squared algorithm to an n squared algorithm, it doesn't really change the fact that it's n squared. Yeah, in a way, you kind of get some like fluid dynamics going on. Yeah, that's cool.
Are you applying force on collision, or just not allowing them?
I'm just not allowing them to collide. Yeah, that's kind of fun. So there was actually a few things that I had to combat as well. I guess what's interesting is that
Like external tractor thing, like you getting dragged off. That's it.
Let's see what happens if you let it run for a little bit. There is no like concept of center of mass in here, but we might play with that today.
I mean, if you program it I'm going to quote correctly, shouldn't it sort of act like it has a center of mass?
I believe so. But it might be, in this particular case, it might be a factor of, so we're not using, well, I mean, technically they're all moving, and because of the collision detection, maybe that's what I need to do first. Let's detect collisions up front. Their radiuses are kind of interesting. I don't feel like the radius is actually doing what it's supposed to. Maybe that has to do with the scale. Oh, maybe that's why. Let's see if we increase this, if this makes more sense. Yeah. That solves that problem. That means they're still too big. So let's go up here to reset. The way that I was setting the radius was some function based on their mass. So maybe this will keep them in the middle of the screen somehow.
Like before, they were just hitting some constant velocity.
There is actually a maximum velocity that they can travel. For good reason. It's the whole concept of slingshot. How many people watch sci-fi? And at some point, I feel like every sci-fi show tries a slingshot strategy to solve the problem. Because if you get too close, then what ends up happening is that the acceleration is it's 1 over r to some power, normally 1 over r squared. So what I actually ran into today was if they get too close to each other, then technically the radius, the distance between the two objects would be less than 1. You raise anything that's less than 1 to a power, it gets even smaller. And if you divide by that, then you get a number that's starting to approach infinity. And so I actually made sure that the minimum distance was 1 in between the objects in order to combat that.
Yeah, I think homework 1, I did like gravitational, like sun at the center, and I basically just had to like, okay, if the force that's like being part of these particles is greater than that, I'll just cap it.
I think it's kind of fun to see the eddies that kind of show up, especially in the initial. They just start spinning wildly around each other. So this kind of also clues us in that if you kind of make this modular, then you can kind of like add stuff in or take things out, as options if you don't want them. So like the collision instance, modeling, for instance, we have that so that it's we have that so it's something we can take in or out. So one thing that we were, or one concept, so let me just put a background over here, right? So we're talking about operators, and so the different kinds we could have are like gravitational operators. This is actually what I did over here. And just for convenience, I'm going to write these equations on the board. So just as a matter of practical advice, whenever you're doing math, like technical writing, the equations take a long time to type in. Because you got to does this look right? Is this correct? Especially if you're copying. So kind of an advantage when I do the little hybrid topics videos because I can write them out. And then it's like, yay! And then I have to remember later on that I'm going to copy all those equations and try and put them on slides, and then it's like, okay, that's actually some work. So I apologize because I really wanted to put them on the slides, but I think retroactively I'll put some of the stuff in the slides. Because if you didn't notice, when I compile the presentations, I also create a reference sheet that goes along with it. So instead of having to look through a bunch of slides, you can just look through a reference sheet with everything on there. Because there's no like required reading, but I thought at the end it'd be nice to be able to have at least a bunch of takeout, stuff to kind of use as a reference, and maybe over time it'll work into something better. But so here's the anyway. So here's the idea here. We want attractors. Okay, so the first one are acceleration operators, and the first one's called like an additive accelerator. What do you think an additive one does? Adds. Okay, we're like adding force to our particles. Okay, so a lot of times the notation we'll use plus, so it's a plus operator, and then that's basically the notation for an additive accelerator. Okay. So what's nice about the difference between these and the velocity ones is that the acceleration ones typically tend to be physically based, okay, to some degree. We're going to see real quick how we can make that not so physically based. But if you have an additive operator, then overall you might have like several. So just like the force diagram, we want to find out what's the net result of all these forces. Okay? So we might have just the sum over k operators. And what this means is that we're basically applying the kth operator to our ith object. And that's the idea there. And so then what we want to do is we want to create a new velocity afterwards. So what we're going to do is take our ith velocity and add the net acceleration times h. What do we think h is going to be about? Yeah, time step. Pretty easy. Okay. All right, and then there's a different kind of operator that it's like a function. So a op we're going to call this, I don't have a good number of subscripts, so we're just going to call it J. And this is a function of whatever the new velocity was and the current. So these ones over here, we have slightly different acceleration operator, but they're functions. Okay, and so we may say that our nu also is the sum of, say, the jth operator on whatever the current velocity is. So these functional operators are, so we just apply them consecutively and to get a final modified velocity. All right, so we just basically just keep piling this stuff on. And before we talk about those, we're going to talk about what are they? Well, I guess we won't leave those undone. We'll just call them what might we want to do with this type of thing. So we have our additive operators before, and then now we're going to calculate a new velocity using these operators. what might we want to do with those? So our gravitational stuff's up here, different things like that. But we might want to have some functions. I guess the question is, what can go wrong? Just add forces to stuff.
Well, I mean, there's the good old like integration structure being messed up. We're doing time steps. The forces aren't constant over time steps. That's why we're re-adding them. So
Yeah.
we just have our integration be off. So we can correct for that.
Could correct for that. Another thing you do is like do things like velocity limiting. So, or you might want to limit velocity, or you might want to make sure that you have a certain minimum velocity so that things don't slow down and stop, or that things don't speed up uncontrollably and just go, you know, go crazy. So that's what these things are for. I like to call these the not so physically based ones, and these ones are probably more physically based. Like we actually have some kind of physical model we're trying to follow. Okay, so this is going to cause a mess, and this is to help clean it up a little bit. In fact, I had to do that with this code. Okay, so as an example, we'll talk about gravitational attractors. Okay, because they're some of the most fun, I think. All right, so you might have some force, and we have G times M1, M2 over R squared times a vector X, which is the direction towards A, or towards object I. Is that M1, M2, or is that MA? Okay, so that's kind of like the general rule, but as with anything, I feel like the book is always on a quest to, let's generalize that. Who says we have to like obey the law of gravity or anything? So they kind of morph this equation to a function. So first of all, we want acceleration. We don't want a force because we'd like to get that out of there. So what we normally do is we'll divide out the mass, right? Force equals m times a. So we'll divide out the mass of the one object of the object that we know about. Okay, and then we'll end up getting, I guess that's technically minus g. So what we'll end up getting is, so here's what they did. They basically said that gravitational constant, you could just, because you want to pre-calculate this stuff as much as possible, but they said, well, you could just factor that in. You could just factor all of that in so that you just have this. Okay, so you just factor all the masses out, and that'll get you your acceleration. All right. Now, they said, well, what does that squared thing do on the bottom? What does that squared thing do? So, the first thing they note that we'll just get the masses out and stick them over here, and then this acts like a strength. Like how strongly attracted are they? And then the one on the bottom is right. So then they said, well, how about we just say that gets raised to some power, because we can get some. There's some things I haven't tried. Like they said, if you set it to 2, then you get the gravitational thing in the normal sense. But they said if you did -1, then it causes the operator to act like a spring. That might be interesting to try. We're going to have to try that one out. Okay, so actually that is true though, because well, kind of true. Because if you don't put the negative sign in front of the G factor, then they all start like, we're just gonna like fly away. So let's go ahead and play with that. Let's go ahead and play with those real quick. So we have the operators there. And one thing that's kind of annoying me is I shouldn't have to come back to my simulation and wonder where all the kids have gone. They have left. They're running away from home. And so we're going to put a fence in. All right. So I guess I could put it into detect collisions, but I think what I'm going to do is bound particles. I'm just going to create a function called bound particles, and this is a great time to start copying and pasting.
Careful. Copy and pasting is a very powerful, dangerous.
Indeed. Okay, we're going to start copying and pasting stuff. So we have our state vectors. So I'm going to go ahead and say that, okay, clamp sv.x. I needed to do something else. This is another thing that's bugging me. So we'll just create functions to kind of, we'll call it clamp3. And what this function is going to do is we're going to return, we have another clamp value, but we're just going to go ahead and clamp this to, we need to do each one of these components separately. So we need an X and a Y and a Z. So whenever you run into this stuff, just, oops. Yeah, you can do that. Just doing a box. Now, if you're doing JavaScript and you're like, I really wish I had the special notation like I got in TypeScript. If you're using VS Code, it'll like, if you use the JavaScript, it'll spit it out for you. This is so cool. So I can say that this is actually a vector 3. Okay, and this is a number, and this is a number, and it'll actually do the work for you.
Is it restricted to that, or that's just something we'll help with?
It'll basically, now it'll like squiggly line it for you. So bound particles. So actually now I can write this clamp3. At some point I need to put this in the library because this is handy. sv.x, and let's just say keep it in -5 to 5. I don't know what that is, but now when we update, after we detect collisions, we can do, actually maybe what we should do is bound the particles and then detect collisions. They're going to be going in and out either way. Something is going to happen. So once we've saved this, they should all stay in this local area. Let's add let's give it some default values. Then later we can just specify. So they should all stay inside a box. All right, that makes it helpful. Now we can see what they're doing in the long term.
Would it be more efficient to do like the clamping when you're like actually like calculating the forces and then updating the velocities and positions, so you don't have to iterate over each particle again later?
It can be, but I would warn Ben against. I don't want to do too much premature optimization. Like it probably does make sense to do that, but right now we're just kind of experimenting. And since we want to, this is one of those like form over function kind of thing. So if I was doing this in C++, the code would look maybe a little bit different than if I was doing it in JavaScript here, or testing things out. It might be that whatever you're using to bound your model though is you might want to change how that's done later on. So then you want to get rid of the coupling to some degree. And two, if it's really just there to keep corner cases from showing up, then it might be something you want to remove later for performance reasons. So there are some good reasons to kind of keep them separated. Okay, so now let's see what happens. This is getting exciting. For some reason, it feels like it's a fluid of some kind. All right, like soap bubbles. Yeah, this is fun. Okay, so now I'm like wondering. So the accelerator operators. Let's try -1, because I'm curious if they do start acting like. I must have something flipped inside that equation, because now they seem like they're trying to stay together. Okay.
Well, because the farther they get from each other, the stronger the force is.
This is where it is. Okay. So, okay. So now if we have this, they should be freaking out, and for some reason they like the corner. That's
Well, eventually they'll all go to the same.
Well, I mean, that's the standard of charge, right? Like, charges will concentrate at points.
Yeah.
Because they're all trying to avoid each other.
So hit reset.
They're all fusing on that corner.
Well, I mean, isn't this the whole idea behind like the way the galaxies are? That because they're not uniformly distributed, they're you don't get like uniform. So yeah, you could tell where they were generated that there was the symmetry, right? This one's more symmetrical. Why some of them aren't going to the middle though? That's kind of. I guess that's just the way that the sum of the forces are. So if you want it said they would act like a spring though. So let's see if we change this parameter though. Whoa, that was very strong. Okay, so let's do 5e negative 11. That's approximately what the gravitational constant is. It's like we're watching paint dry. So originally I was using the gravitational constant in there, and then I was like, is anything happening at all? And so then I actually changed it to something, I think like 5e6. Let's see it. This is, okay, this is actually doing something. Why some of these aren't like repulsing, like that are neighbors, that sometimes it's kind of. But I guess it's the whole. It has to do with the distance to the hole. Let's up that r squared value, and let's make it faster. This is one of the cool things about physical simulation, or not so physical simulation, is just playing with the interaction of the parameters. Reset. go back here. And then there's other things that you can do. Like maybe we could say that if in the bound particles, you know, this is a great time to if old dot, I think this is a function. So now we're saying.
Oh, that's cool. I see like a circle from.
Yeah. Oh, yeah. Because they're being randomly put in a circle.
Oh.
That's cool. You know what this reminds me of? I was watching Star Trek the other day, the Borg episode. Now I used to love watching Star Trek: The Next Generation, but the first season finale that they had, the Borg, where Picard became Locutus, they had this saucer separation thing, and they fired off all these discharges, these antimatter discharges, and they're like just kind of going randomly, and that's almost what this reminds me of when they're just like randomly going off in those directions there. So this is so yeah. Let's multiply this first by a random number so they can be anywhere. Let's say anywhere inside the box, and then we could say that they start out with maybe they start out with a random velocity, but that it's very tiny. Let's see what happens. Reset. Okay, that was a standstill. Oh, okay. Dot scale. That's because we didn't do it the right way. Fun. So this is another reason why you might want to have like this is kind of what this is doing. We're just kind of adding a random. In this particular case, this accelerator function is saying if it's outside the bounds, create a new one with a new random velocity, and essentially just randomly place it. Okay, so then we can see, well, what happens if we then change it? Oops. Let's use, say, -1. Yeah, you get different. That's cool. Oh, another thing we could do is we could say, let's not do any collision detection at all. Because the collision detection is going to limit the way that the particles behave to some degree. So, in other words, it's very hard for particles to go like this if they're the collision, if they have to like go around the other object.
I feel like it matters less for when we have to repel a case like this compared to the contraction.
Yeah, this is true. So I guess if we go back to our bound particles and let's just go back to clamping it so they stay within. All right. Why it gets lopsided? I think it has to do with the center of mass. Like the. Let's go back to the gravitational and see what happens.
In fact, they're not repelled. They're not impacting each other anymore, so these are all concentrated corners now. That's the
So we now wire this.
That's a good question.
so we changed how gravity works.
It might be that we're doing this wrong. Oh, that's what we're doing wrong. That's what I'm doing wrong. I should be taking the max of R.
Maybe now we get rid of that negative sign you originally put.
There we go.
Okay. So it said this other one would act like a spring, producing an acceleration of particle I that is proportional to its distance from the attractor.
Yeah, because that just turns it to that constant times distance.
Yeah. So okay, so now I guess now that we got that, okay. My original thinking that the negative value had to do with the fact that the direction that I was getting is just opposite. So okay, so let's try the -1 out now and see what happens. Now that theoretically should be. So now they're acting like springs. And yeah, got it. Pretty neat. And then we can add the collisions back in. That's cool.
Now we just need sliders and buttons so we can change them or whatever.
Well, that's cool. What's cool about that is we can actually do that pretty easily. If you set up stuff to kind of help you write this stuff out, then let's put call it G, and it's maybe we say it's normally 5e minus 5, but it can go from 1e from 0 to actually 0 should be the max. 1e minus 6 and one e minus 4. Go from there. And P is a value that starts off at 2 and can go from -4 to +4. And if we save that, in our update function, we say get range value for put that in there. Yeah, we're gonna see what happens.
Is there a way to display the numbers those are currently set to in a reasonable way? Because that's one of the things when I was playing around with sliders. I was like, I'd like to see the number next to this too. Or on the.
Yeah, there is a way to do that. Let me take a look at the HTML utilities. The create range row. Well, I think what I have to do is add a function that it has like an on change. But what we could do is, so create range row. Let's see here. If not is vector. We could label ID equal and then we're going to call this so this is how you would do it. Let's see if this does. Okay, so yeah, so that's
I presume somewhere in the Vexor library there's a wonderful, easy put text into simulation option.
Well, here's what we're going to do here. We're going to say ID plus underscore value Now this will break, it's going to break any code that has a vector in it. Actually, there we go. If we have it. Okay. So yeah, we may want to create a bigger version of that. So we have yeah, okay. That's how it's done. That is how it's done. Okay, so then we can get rid of this. And I guess we may want to make that so it can be bigger, technically. Okay. Let's make it so that the p value doesn't have to be like an integer. That works. now if we want to actually add collision to it, get range value collisions.
So just getting the range value of fast operation.
We're going to find out here in just a second. I don't know that it is. Seems to be running pretty smooth.
I guess since we only asked to do it once, it's probably not that bad.
Yeah.
They didn't do it a lot.
Yeah, well, another thing we could do, and that we are going to do, is like exercise in how can we make this more efficient. If this dot when we hit the reset button, it's probably a good time to do that check. Although we won't get the because I was actually thinking to myself we could do we could even change it so we can use as many objects as we want. So, maybe start with 10 and go from 2 or 1 to 500. Okay. All right. Then we know if we hit the reset. Yeah, somehow our collision detection thing isn't. Okay, that's looking pretty good. Now we got collisions and I'm going to call those quantum states because, you know, that's right. In fact, part of me wonders if quantum theory really isn't just freak out of nature when it can't determine if a collision happened or not. And it's like, fine, you guys are right here. You guys cannot come any closer, or I'm just switch you. That could be some element of truth to that. That's right. The
fact that quantum effects seem to very much insist that you're not allowed to find out anything about this.
That's right. You can't
question everything. Like, wait, you attempted to make an experiment to figure this out which way the photon went? No, I'm going to erase that information back in time.
Okay, cool. So this is another thing that they mention in the book is that you may want to add random accelerations. So I thought that's kind of interesting. So you could have you could simulate a turbulent process. So that might be interesting to try. Let's give it a go. Let's see what happens if you do that. And maybe we'll give it a sure, we'll do it in the system dynamics. It might be something you want to put somewhere else, but this is where we're going to do it. We're going to say if math.random is less than, let's give it a 1 in 1,000 chance, because this is going to execute every single frame. So sv.a equal s. So let's just say we do give it a random acceleration. Then we just have to watch for them. Or we could add another flag. Oh, I have a good idea. This is another way of doing a flag. We can create a variable called random accelerations. And we'll say it's 0. Call it random A. So this will be fun. So we'll say it can go from 0 to 10. And I might call it random X to kind of give it a so that it can happen between I'd like to give it like 1 in 1,000 chance or something like that, but we'll call it P, probability. Okay, this can go from 0.0 to 1.0, and we'll just give it a small step. Actually, I guess that should be okay. Random P. This is how you get like this combinatorial explosion in your oh yeah, I think you're right on that. Okay, we'll start over here, and so now inside our system dynamics, if random is less than this dot random P, scale by whatever random A is. Okay. just put some numbers in here. Yeah, there's some jitteriness going on because we are doing like a random, almost like a random impulse in a way. Although technically that it's being erased by the gravitational element. Let's see here, reset. But the idea here is, you could simulate like snowflakes. So if we increase the number of objects, I guess technically if we called P0, would that get rid of our we need to turn off the collisions. Or can we? I don't think that's working right, 100%. So yeah. So now we can kind of add some turbulent motion to them if we wanted to. Maybe we'll say that if it does happen, it's violent. Yeah. Okay. Now, another thing you could do, like when you're trying to update the times and stuff, is we could control that by saying if so much time has elapsed, then update our current states and stuff, right? Okay, so that's pretty cool. We're doing a lot with this. Then there is drag and undrag. So basically, the operator there is to so you might have like a velocity vector. We were doing this last time, where maybe that's something we could do in our. Should we try and add drag? That could be interesting. Okay. Drag. So this is a case of we have, I'm just going to reuse it for here. Drag equals, we have whatever our drag coefficient is over the mass of our particle times whatever the wind velocity is minus the current velocity. That is the that's how we basically add drag. So essentially, we could do that. Although, I think that'd be more fun if we had a way of specifying what direction the wind was pointing in, which we don't have right now. So I'm going to wait on that one. We'll wait on that one, but this is how we would do it. Okay, so we could just add that that component of it's basically like adding, the opposition force. But theoretically, you don't have to have D as a positive value. You can have a negative as well, and then see what that does. And so they say that this creates undrag. That is a force tending to increase the speed of the particle. So in other words, if it's just kind of like staying steady, this will like give it a nudge. Okay? And so I think this is a case where the velocity limiters where you have like a minimum velocity and a maximum velocity kind of come into play. But they said that as long as you're doing undrag, the particle will increase in speed. So they normally do that only for a short period of time until you've gotten to the velocity you want it to. Okay, so they said used in this way, it is a good way to smoothly increase the particle speed. So there's some times when you want to undrag an object. Okay, so then the velocity operators. That's not in here. So the velocity operators are a case of you can apply just like straight linear operations like translation, rotation, and so they actually use that to illustrate vortices. Okay, now I don't think we have time to talk about vortices today, but at least not anything more than like theoretical. But I do want to talk about that, and we are going to. So we'll talk about that and collision avoidance before we end for today. Okay, so here's the idea behind vortices, which I thought was very cool. And I may just implement this week because I think it would be fun to do it. So the idea behind vortices is that this is a velocity operator. Okay, so we looked at acceleration operators. In fact, we kind of got lost playing with acceleration operators. That's probably the only issue with this class is you just get sucked away like changing parameters. Like, oh, it wasn't what I'm supposed to be doing. Okay, so here's the idea behind a vortice velocity operator. So they want us to imagine a cylinder. And inside the cylinder is where all of the interaction is taking place. So I'm going to draw an axis through here. Okay, and this axis is the direction of the vortice. Okay, so we'll just say B tap. And the idea here is we have a particle inside the vortice somewhere. So what we're going to do is we want to take this is, I guess, technically the center of the vortice. So we'll call this X, B. So I'm going to use X for positions, V for velocity. And we want this vector here, so we're just going to take, I guess you just take the direction from X sub I to X sub V, and that's going to give us, I think they call that vector X VI. And so we're going to use this function to, we want to figure out how much velocity we should give it. Okay, so things moving in the center should be moving faster, right? Things outside should be moving slowly. So what we want to do is project that vector onto the axis of rotation. So in order to do that, we have to use a dot product. So if we're going to find out what the length here is, length I, then in order to do that, we can take the dot product of the direction of the vortice minus, or dot product with the vector x vi. Okay? And it's not normalized because we don't have the hat on it. So this is how we find out what the length is. So we're basically projecting this vertex onto this other, projecting this vector onto this vector. All right? And then the only thing that remains is to find out how far away is the point from the center. Okay, so that's what we're doing here. So the next And we actually want to find the vector. So in order to do that, we will take this vector here, x vi, minus L sub I times v hat. This is actually a really useful operation for a lot of things. Okay, just knowing how to project lines onto other lines and find out how far away they are. All right. So now that we have the vector going from the center over here towards x sub I, then we can use the length because we're actually just interested in the distance. So if you just take